let's start kicking everything for you.
By the time the
So when we 9 to 8, let's do that. After we have done, we'll string the stochastic simulation. Now we'll be concentrating our effort on calculating the soil response when the earthquake is propagating through a layer of soil column, right? So during the earthquake, and we assume that the soil column is present, and then the wave is propagating, or the seismic wave is propagating through the soil column to the surface, right? So that means from the rock site to the surface. So underneath the soil there is a rock. So we are basically assuming that it is propagating through the soil and it will come to the surface and recorded at the recording instrument, right? So that's the part. Now, when the soil column, as it propagates, then the stress which has been generated during the earthquake, that has produced some strain into the soil column, and that strain wave is actually basically move from one point to the other point through the soil column, right? And the wave undergoes some sort of a damping. So yesterday we have talked about that there is a geometrical spreading, and also there is a scattering effect as the wave energy gradually decreases from the source to the site, right? So similarly, those concepts will be bringing in, and then the soil column also has another factor, so that we will be also taking care. That means the material damping part. So that material damping, how it is being related, what are the mathematical equation of material damping, these will be discussed, right? And then ultimately we will be seeing on a different type of soil on the rock, and how the mathematical equation is this, that we will be doing. And then in the next week sometime we will be giving you a software. It's not the coding, it's basically the software. That software you will be using, or you know how to use, and then that will be used for to compute the transfer function of the soil. Now, what do you mean by transfer function? If there is a soil column, underneath there is a rock, we assume that the earthquake has happened into the rock, and then when it transferred to the soil, it will have some changes in the amplification, right? So that is what we call it as a transfer function. So if you know the soil transfer function, so then you do not need to know many other things, because if you know the earthquake, say suppose Fourier transform of an earthquake, recorded data, then you can multiply it with the transfer function of the soil, then you can get what will be the Fourier transform of the recording station at the surface, right? So the transfer function of the soil has to be known, and if you know that, then you can generate whatever the earthquake type you want, just multiply it with the transfer function. You will be getting the recorded spectral data on the surface, right? So that we will be doing it here today. Let's see what we have. So first of all, we try to apprise you about the material damping. When a stress wave passes through the soil, then what are the damping it will take place. So the whenever any elastic energy or the earthquake seismic wave is propagated, then it is basically in a material, it will be provide some, or it will be generate some heat, right? So if any elastic energy propagates through a material, right, and due to that, there will be the decrease in amplitude because some part of the energy is converted to the heat energy, right? Now, now there is a viscous damping which is mostly we use it to represent this type of attenuation or dissipation of energy. Okay, so viscoelastic wave propagation, which is model as a, we call it as a Kelvin-Voigt solid or void solid, Kelvin-Voigt solid, and this has a elastic deformation. Any soil surface, any soil material will have a elastic deformation, plus there is a viscous deformations, right? Because the soil has some water and all these things. So soil also undergo, in addition to the elastic deformation, it also goes viscous deformation. So, so that is what we call it. We call the soil as a Kelvin-Voigt solid, right? So there is a shear stress. You all know the shear stress, we designate it as a tau. Tau is the amount of shear stress. So in this case, this is on this surface. So we write it as a sigma xz, right? So this is your x and z surface. So this is xz plane perpendicular to xz. So it is called sigma xz, right? Now this will be equals to the shear strain, which is the gamma. So shear stress is basically equals to the shear strain that we all know, and we know that if that is the case, then G is the shear modulus, right? So shear stress by shear strain is equals to the shear modulus. So G is the shear modulus part, and gamma is the shear strain, and but this is not all. But there is a viscous deformation part, and that deformation is eta into d gamma by dt. So that means it is a time dependent part, right? It's a time dependent part of the shear strain, how it is changes with time, and that multiplied by eta, it is called the viscosity of the material, right? So viscosity, so the shear stress is proportional to the d gamma dt and multiplied by eta. Eta is the viscosity of the material, and it is the soil. So the soil will have a viscosity, and that we have to come, and that will be providing this viscous deformation. Now, the shear strain is the change in displacement by the original displacement, original material. So this is your dg. So dg by, so this surface, this length was dg's, and this is the du. So this is the du by dg, right? So this is your change and this is your delta U, and this is your dg. So du by dg is the shear strain, right? So eta is the viscosity of the material, g is the shear modulus, and du is the shear. We call it as a shear deformation, or the shear, or it is a displacement due to the shear, right? So that's the main part. For a solid, for a soil sample, we have this relation between stress and strain. So there is a strain part, and then there is a strain changes with time part, right? Now, so if we assume that the strain which is being developed, this strain is a sinusoidal in nature, so that means strain, since it's a d omega dt, it's a varies with time, and we assume that shear strain for a simple model is a sinusoid. Then your shear stress, you can write G with your gamma, I can replace it with the gamma 0 sine omega t, and d gamma dt is equals to n omega gamma 0 cosine omega t, right? So that's your, that is basically your shear stress values, okay? Now, so let's assume that okay, the stress is passing, but within a cycle of the strain, how much energy is getting dissipated? Because as I told you that the shear strain is a sinusoidal, so therefore assume that it's a sinusoidal. We are trying to calculate in one cycle, a single cycle, how much energy is basically dissipating, right? So that means amount of work done, because work done means it's the amount of energy dissipated. So amount of work done in a cycle, we need to find it out. So that is your del omega. So del omega means it's a G into d gamma. This is your G with your rate of change of the shear strain over an interval of time, and time equals to T0 to T0 by 2 pi by omega. So that means one complete cycle, right? So within the complete cycle, how much it is being dissipated, so that is equals to your delta W. And if you can put that d omega dt, a d gamma dt equals to gamma 0 into sine omega t, you can use that and put that number and do the integration from t equals to t0 into 2 pi by gamma, you get it's a pi eta omega gamma square, right? So that's your amount of energy dissipated per cycle, okay? So this is your each things dissipated energy is, therefore you can see that amount of dissipated energy is proportional to the loading frequency omega, and that is the main factor, right? Now, so if you say that this is being attenuated, so therefore we calculate this parameter, it is called damping parameter. So that means as the wave propagates through the soil, it gets dissipated, so that means it gets damped, right? So this is your damping parameter, and that is your known as a zeta. So zeta will be equals to with a 4 pi solid angle, so it is 1 by 4 pi delta omega by the total value of W, right? So that is your damping. So that means 1 by 4 pi, because this is your full circle. So it is your 4 pi solid angle. So that's your delta omega by these values, right? Now, so peak energy stored in a cycle it is W, that is equals to half G into amplitude square, because there is a kinetic energy and the static energy. If you can say that this is only the full part, so that is equals to half part of this G omega gamma square. So this Chi value you can calculate, 1 by 4 pi, and delta omega we have calculated as a pi n omega into gamma square, put that number, and this will be equals to half G omega square, so n omega. So if you can calculate that, this your gamma value or the damping value comes out to be 2G omega by Chi. When keep this number in your mind, we will be coming back to this equation afterwards. Okay, so eta will be equals to twice of the shear modulus divided by loading frequency into the zeta. So that is equals to your the coefficient of viscosity of the medium, right? So it depends upon the damping of the solid, right? So is it okay up to this much? Is it clear? Now, so if you know that our one-dimensional wave equation is equals to mass into the equals to the m into du dt square equals to this is your change in the shear stress, right? So delta G of this one. So so this delta xg delta xg is basically, we have said that it is your shear modulus into the multiplied by the shear strain plus the coefficient of viscosity into d omega dt. So dg dt equals to this part, right? So therefore this is the dg dt, and then sigma xg is basically du by dg. So du is the deformation, so du by dg, and then eta d gamma dt, so d dt of this gamma equals to again du by dg, right? So if you can break these things, so rho into del u del t square equals to g into du dg square plus eta into, this will be the d cube into this one, right? So this d, this d, this d, so it's the d cube u into d2j into dt square. So this is our equation of a Kevin Boyd solid. So then that will be equals to this one. Okay. Now this is a u is the deformation or the soil deformation. That soil deformation is is depending on the two type. One is the ug, so that means with the depth, and also on the time part is there. So this is your one-dimensional wave equation, and its solution you can find it out like this way, right? Just variable separable method, you can see that. Okay. So you know how to solve this equation or not? So this equation you can solve it if you just do a del 2u by del t squared. So then it will be only the omega square comes out here, and then if you do this part, that means the g part, then the g part will be equals to g into I omega n into del 2a by del g square into this part, right? So you first calculate with a d2u dt square, so all the omega square will come out. So the I omega square and I omega first, and then the I omega again. So basically u delta u by del g square, or du by dt will be equals to, according to this, it is e to the power I omega into t into ug, right? And then if you can, into I omega, right? And then du dt square, if you do it again, then it will be again the I omega. So it is a minus I of I. So this is your I square. So this is your I square omega, means it's a minus omega square, and then this will be equals to u, right? So du dt square equals to this much and multiplied by omega. So this is minus omega squared, this one. Now if you do it as a du g dt, du gt with respect to your z, okay. So these things, if you can do it with the g, then it will be the d capital U dg into dg, right? And then if you can do it again, then when you can find out there is a I will be here, one I will be always like this, right? So that you can calculate and make it out with your, sorry, I take it back. This thing will not be here. So this will be equals to du dg square will also be equals to your du square by dg square, right? So then you can substitute it here. So here there is a 1t, so therefore the I omega will come into eta. So this will be like this one. So g I omega n du g square into this part. Now these things, since it's a real part as well as a complex part, I call it as a complex shear modulus. So this is what we call it as a complex shear modulus. So complex shear wave or the shear modulus, this will be equals to g I omega n. So that means if we can take out g outside, so this is 1 by I omega n into g. So I omega by g, so that will be equals to xi. We have already defined it. So this will be equals to 2 ij. So g will be equals to 1 plus 2 ij. So that is equals to the complex shear modulus. So the shear modulus equals to the g plus 1 plus this one. So that is another complex shear modulus expression. So apart from this, so that means g prime will be equals to du dg square into rho into this part. So this has a solution ugt will be equals to a into e to the power I, because this is the wave equation. So this is the equation of the so that means at each depth with the time t, what will be the equation of the solid, it will be like this, and then this k prime equals to omega into g prime, and g prime, because g star is also have a g into I omega n, so you can put that thing so that we can also express k prime, k star equals to k1 plus ik2, and k1 and k2 are the roots of the two complex numbers, right? So that we can calculate it, and we can express these equations like this. So therefore the k1, if you can substitute this k1 from this equation, so k1 will be equals to this expression, and k2 will be equals to this expression. This is the same expression, just only plus and minus will be opposite. So this is plus 1 and this is a minus 1. So if your k1 is equals to 0 and k2 is less than 0, so we have this equation for the wave propagating in a positive g direction, right? So this equation is e to the power k2g and e to the power I omega t minus k1 into g. So k2 is negative. That's the material damping is exponential in attenuation, and because k2 value is coming out to be the negative value, and this will be the and it's a exponentially attenuate with the distance. So with the distance, this part is exponentially attenuated, and then this is your time domain part of the wave propagations. Anybody has any questions for me? Okay. So this is your one type of damping, which you call it as a material damping, which is due to the Kelvin void solid. So there is a stress wave as well as the viscous damping, right? Now, there is a radiation damping also, that this radiation damping decreases the wave amplitude as it travels the distance. So this is some sort of this is a type of the geometrical spreading, right? So that is the geometrical spreading. That means as it propagates from one point, it gradually decreases, no matter what has happened to the other things or other type of damping. If it travels from the spherical wavefront to the cylindrical wavefront, gradually there is a geometrical spreading, right? So, so let us assume a solid and a solid with a conical separate rod in front of a stress wave. So that means this is a stress wave is coming, and there is a conical separate, or might be it will be showing like this way. This will be a conical separate surface in front of the stress wave, right? So that how much is the change as it travels from here to this side of the conic. So that will be giving you the radiation damping or the geometrical spreading, right? So let us assume that this apex angle on which the wave is incidenting, so that is your some sort of an angle. So that angle we call it as an alpha, but to the normal stress and being a uniform this one. So let's see, I can give you the next picture is here. So this is your alpha. Let's see, this is a very small solid surface we can assume, and let's see this. So that means this is one surface of the conic. This is another surface of the conic. So in between these two surfaces, there is a distance is dr, and wave energy is basically coming from here, and energy basically leaving here. So this is equals to rho into the volume, right? So rho into this one is equals to mass into acceleration. So r square dr is the elementary r distance, and with a dr thickness, how much is basically the volume. So volume multiplied by the rho is basically the mass, and that mass is basically taking here as a du dt. So mass into du dt square, right? And then that is your stress. So on this side, this is the sigma. On this side, this is delta sigma by delta r. That means the stress delta sigma by delta r into delta r. So that's a change from here to here. And then that will be equals to the total distance from here is equals to r and r plus dr. So that is square. just like this one, r square. So this is r plus d square into alpha. So this will be writing there alpha, and minus this is your change. So change equals to same thing, sigma r square into alpha. So therefore ultimately we get this equation if you do the division, keeping the rho and 1r outside. So then that will be basically the radiation damping, right? So so if you know that the normal stress strain is equals to the Young modulus, so that means in this case the sigma equals to E into du dr, because the Young modulus is equals to longitudinal stress by longitudinal strain. So that is your sigma by du dr equals to E. So that E you can substitute, that sigma you can substitute it all this equation, and then rho r into du dt square, r into, this is your d sigma by dr. I can write it as a sigma by E, and then we can rewrite the equation in terms of the Young's modulus, right? So this will be equals to, by integration rule, you all know that if your rho and r, rho is the density, so if you can divide by the rho, so E by rho, and this r part is basically we are trying to calculate del to u by delta t square. Okay, so we take the r inside this one. So this is du by dr into dt square, and this will be also du by dr and dr square. So this is your time domain part, and it is the s or the distance domain part. So this is also a wave equation, and this wave equation indicates this is the velocity. So this velocity of this thing is basically E by rho. Okay, sorry, velocity will be equals to E by rho. So that is your shear wave velocity. So you can calculate. Sorry, this is the longitudinal wave velocity, E divided by rho, and you can calculate that number. So this is your radiation damping, and the solution of the radiation damping is this: U r t equals to 1 by r, Vt minus Vr and Vt plus Vr, where V is the propagation velocity, r is the distance, and this is the wave equation, and it will be decay by amount of 1 by r. Okay, so this is what is called as a radiation damping due to the solid part of the soil, and then there is a viscous part is present with a viscosity in the solid that we have also need to take care. Now, in addition to the damping by material damping or by viscous damping, the elastic damping, there is a radiation damping which is due to the spreading. Then there is also in a soil the wave gets scattered, right? So basically the soil particle is composed of various scatterer in the medium, right? And this scatterer, if the wave comes here, hit this scatterer, it will go on scattering all over the place, right? So that effect, we call it as a scattering waves, and that's each scattering is also reducing the wavefront, right? So the amount of energy is also being lost due to the scattering event. Okay, now we can see, let's see, there are two material 1 and then there's material 2, and on the other side there is also another material 1. So that means material 2 is sandwiched between material 2, material 1 on the both the sides, right? Now, if you can say that across the boundary, the main thing is this, that across the boundary the displacement is continuous, right? So that's always the case, because the amount of displacement produced by this part will be the same as the amount of displacement produced in the next part, because that way there is no accumulation of the stresses at any boundary. So that the displacement is therefore continuous. So if we assume that this wave, which is incident, is basically uxt, then this wave which is reflecting, it is a urt, right? So unxt and urxt. So that means we are trying to calculate with the distance how it changes, and with time how it changes, right? So u as a function, or the displacement equation as a function of x and t. So similarly for the reflected function, this is also x and t. And then if the displacement is continuous, means at this boundary, whatever is the displacement, that will be the same as this boundary. Okay, because these two are similar metal, so similar material, so we can always write that. So so first of all is the n one layer case. So unxt and unxt will be equals to ui2 plus ui2xt. So I2 means the sum part. So this will be incidenting on this material. Some part will be reflect out, and some part will be transmitted, right? So the stress continuous, because across the surface the stress is also continuous. So if you can do that, so that means this is the same equation, that this much of energy is going there, this is coming back. So that will be equals to u1xt, and then this one is equal to v into xt, and the displacement velocity, sorry, I take it back. This is equals to I omega t, and this part for the incident part and also the reflection part. So if at x equals to 0, if I substitute it, then this is a plus ar equals to b plus br, right, at x equals to 0 point. Now similarly the stress is continuous also. So stress is basically the du by dg. So you can write down the du by dx, sorry, here it is the du by dx. So if you can write it down, for this part it will be this one, for this part it will be this one, and then for the second part it will be these two. And if you can put at x equals to 0, this will be the continuous part will be equals to this part. So this is one equation, this is another equation, and so that will be done. And similarly on this boundary we can also write that this is u12, which is coming from u1 to u2, and then it is a reflected back to ur2, okay? So ui2 and ur2, and from here it is only c, because this is your infinite, so it will not coming back, right? So u3xt, and that at x equals to L, because this is your L distance, x equals to L, everything looks like this. And similarly, if you can take the stress part, then stress part is equals to, between this surface, then stress part will be equals to this one, right? So if you can take this 4 equation, and I am trying to understand that if it is a C and if it is an A, so what is the ratio of the C and A. So how much C you can get for how much of A. So that means C by A. So that you can calculate from this equation and then substitute all the parameters. You can get a C by A is this relation, and the impedance ratio of the second medium you can also calculate. It is a K2 M2 by K1 M1. So that means this is the rho 1 V1 by, sorry, rho 2 V2 minus rho 1 V1. Okay.
So what is this? I am here.
So this one, and then as I discussed last time, that that there is a scattering. So this displacement amplitude ratio, the C by A, that is what we are interested in. So that means one material, the A is incidenting, and then from the other material C is coming out. So that means C by A, that's the displacement ratio, is depends on the impedance contrast, right? So that means whatever you can write, it is basically depends on the impedance constant, and the inclusion of the relative length is important, right? So what is the length and what is the impedance contrast? These are the two things we are trying to measure, and based on that time, last time we had said the quality factor or the attenuation part. So, and also important thing is this, in this part, there is a L, that means the length of this two material, and also it will be depends on a factor which is called L by lambda, right? So L by lambda is the wavelength corresponding to the length of the scatterer. So L lambda ratio, so this is your impedance, transmitted wave amplitude decreases with the increasing of L lambda ratio, right? So these are the scattering part and the damping part, which is basically important for the soil when these waves are incidenting, right? Now, if you see the incident as a SH wave in the medium, say suppose this is the first medium, so the wave comes and then it is a SH part. So as I told you that the wave can be each point in the space, it can be generated S wave and it can generated the P wave, and whenever there is a S wave generated, there is a possibility of SH wave and SV waves, right? So if we are incidenting on the SH wave into this one, so this is the incident SH wave with a no particle motion. SH means it's a basically the horizontal motions, right? So horizontal motion means the direction of propagation, and the particle are basically in a horizontal plane, and vertical are it is a vertically polarized with the direction of propagation. So incident SH wave with no particle motion component perpendicular to the boundaries. So the transmitted wave is actually, so there is a refraction took place, right? So that refraction in this inclusion layer, so that means it is a medium 2, and it propagates beyond this inclusion at a different orientation, and then come back to the material again, and then reflect back, right? So this is your SH wave part, and similarly there is a P and SV wave are two different part, and that also will be getting generated. But we are in our transmission layer, we will be only considering the vertically propagated SH wave, right? So that's the only thing we will be interested in for the soil sample, right? So 1D ground motion analysis. So what has happened, that this is your bedrock. In the bedrock, and on this type there is a soil, right? So this is a sensor. This sensor is located onto the rock at the borehole, and this is a sensor which is located on the rock but at the surface, and this is a sensor which located on the soil at the surface, right? So basically what is happening, that we are trying to understand that if it is a soil is there, then how much amplification, and if it is a soil is not there, so that means these are same, then how much will be the amplifications, right? Because these are the rock samples and this is the soil samples, right? So, and we are assuming all the layer samples are basically, it's a horizontal, right? So soil sample will be treated as a horizontal layers, and underneath the rock, there is some vibration took place. So just like on the top, there is a material one. Just like on the top, there is a material 1 and material 2. So the material 1 and it is being propagated to the material 2, right? So that's what we like to do, and we are seeing how this equation can be developed, right? So so we are assuming the SH wave propagating vertically, and this is underlying the bedrock, okay? And the soil layers and bedrock surface are assumed to be extended infinitely. So this side, it is extended infinity, and also this side, it is bounded by the rock surface, right? So we do the one-dimensional the analysis of the wave propagation, and let us see how we are doing it. Okay. Now, here we are basically doing the linear analysis, right? Or what we call it as a linear analysis means that the stress produced by the wave is only in a linear domain. So that means there is no non-linearity is happening. So that means the stress and strain are proportional to each other. It is not the strain is the different than the as the wave propagate, there will be the changes in the strain. So that's not the case. The case is this, that the things are the linear, but the linear type of assumption is always not the true, and sometimes we do see the non-linearity. So in order to have a better part of the two world, we will be saying that this soil is being subjected to a equivalent linear analysis, right? So equivalent linear method means there is a certain type of strain changes in the solid, in the liquid we are expecting, and that depends upon the modulus and the damping part of the soil, right? So that we are saying that not high level of strain, but a little bit strain is developed, which is basically depend on the modulus and the modulus of the rigidity and also the damping part of the soil, right? So that is an equivalent linear analysis. It is not the totally linear method. It's a equivalent linear, and then we will be, so that means the non-linearity is or we can call it as a weakly non-linear, right? So weakly non-linear method we will be using here in the analysis, and we are trying to calculate the transfer functions of the material, and that's a so this is what we call it as a equivalent linear method, and we will try to see this one. Okay, now what has happened that from this bottom to the top, the velocity value decreases, right? Because as you know that from the top surface to the bottom surface, velocity increases, but this is the wave which is passes through the very high velocity layer to gradually to the low velocity layer. So therefore, what will happen? Each part it is being going towards the normal, and then it will be coming here, and basically incident on a 90-degree or the perpendicular to the surface of this material, right? So that's your part. So now what has happened that due to the stress wave, each layer has its own frequency of vibration, and it might be possible that due to this propagation there will be some of the resonance effect. So that effect will basically creates a lot of vibration in the soil, and that we need to test that whether it will produce a vibration during a significant vibration of the soil during the wave propagation or not. Okay. So very first simple. Now, for the time being, for the first idea is this, that we assume that the bedrock is a rigid one, right? It's a rigid one, so that means there is no elastic thing is there, so that means there is no propagation. It's a totally rigid material. So if it is a soil and it's a single layer soil, having a thickness h, one layer, rest on a rigid bedrock. And we are our calculation is always we are assuming the z will be positive downwards, and u is the displacement or at the surface. So, and since it's a wave propagation, so we write it as a e omega t plus kg. So this is your omega t plus k with a g. G is this axis, and the down one is equals to the omega t minus kg. Okay, so these are the two parts. And the first part going with a of a, second part is after returning back. So that means this wave goes here, hit this, because this is air, so it will be coming back as a B, right? So that's the part. so basically we are trying to calculate the how much is the horizontal displacement, because we are interested to calculate the horizontal movement, not the vertical one. So u at any the g and t, or at any depth j and having a time t, so this will be the incident wave plus the transmitted wave, right? So or the reflected back waves. So AE omega t plus kg and AE omega t minus kg, right? So k means it's a wave number, and wave number you all know it is the omega by Vs. The Vs is the velocity of the S wave, right? So at the free surface, when the surface is, that means it's a g equals to 0, right? So at the free surface, the shear stress is tau, and consequently when shear strain must vanish, because there is nothing on that side, so it will be 0. So basically tau will be at g equals to 0 and t, so gamma 0 t, so that means d mu 0 t, this is equals to 0. So because there is no shear strain, so what has happened, this is your g, and g into this part into e to the power I omega t, if you can do that. So this is your, if you can differentiate this one, so this will be g I k into this part, and put the z value equals to 0, so that will be equals to this one, right? So that means if you can put that, then this cannot be 0, so only this parenthesis term to be 0, and it will be only 0 if it is A is equals to B. So this is the situation at A equals to B, right? So put that A equals to B here, then what has happened, this UJT equals to 2A into e to the power omega t plus kg, and plus e to the power omega t minus kg, and you can put that, it will be equals to 2A cosine kg into e to the power I omega t, right? So so let's see, we will be doing it after this one.